So let's have a look at how we can show that a linear system does not have any solutions. And let's use the example from the last unit, the example that we claimed had no solution, to illustrate this. Okay, now in this particular case, we're starting with a linear system that has a square matrix associated with it. Notice that this here has as many rows as it has columns. But we could have had more rows than columns or fewer rows than columns. Doesn't really matter. Let's apply a step of Gaussian elimination to this. And we get this. And then let's see, it looks like we're actually doing Gauss-Jordan because we're introducing zeros above and below the diagonal. But notice that in the process, we also introduced a zero right here. And notice that by swapping rows, we can't fix that. As a matter of fact, in this case, there is no row below it to swap with. Now, if we take this and we translate it back into the linear system that it represents, notice that the last equation here says that 0 is equal to 1. Well, for what choices of chi0, chi1, and chi2 is it the case that we can make 0 equal to 1? Well, the fact is you can't make 0 equal to 1, and therefore there is no choice for chi0, chi1, and chi2 that will make that last equation true, and hence this system of linear equations has no solution. If Gaussian elimination or Gauss-Jordan elimination introduces an inconsistent equation along the way, then the system of linear equations has no solution.